Hi everyone, my name is Ellen Fireman and this is the pre-lecture on the two-sample z-test. This two-sample z-test comes up a whole lot because often you want to compare the averages or percents of two populations. So here's a timely example. A random sample of 500 men and 500 women were asked just a few days ago if they thought the charges of sexual assault against Brett Kavanaugh are true. Do you think that Kavanaugh should be confirmed to the U.S. Supreme Court? Now, I was very interested in this and I thought, let's do a significance test, because even if they do find a difference, is it going to be significant? First of all, they can't, so let's think about what they did here. All right, so they had, let's put it into the context of a box model. So the population that they're asking here is all registered voters. And there's two populations here, two boxes, one for males and one for females. This was a nationwide sample, so in each box you can think that there's millions of tickets. In each box there's millions of tickets, and what's on the tickets? It's a yes/no question, so there'll be ones and zeros. All right, and we don't know what the true percentages are of the whole population, so we randomly take a sample of 500 tickets out of here and 500 tickets out of there. All right, now what would be our null hypothesis? Our null hypothesis would be what? That these two are equal. The percentage who say yes for the males and the females are the same. And so we can write that down, so that would be H naught. H naught would be what? That the percent of ones in the mailbox, sounds funny, mailbox, right, is equal to the percent of ones in the female box. That these two are, we don't know them. We don't know them. There's millions of tickets, one for every single registered voter who's a male and one for every single registered voter who's a female. So there's millions of tickets in the boxes, both boxes. All right, we've got that down. Now what would be our alternative? We'll call it HA. Our alternative is going to be what? Well, I believe, just from past experience, that I think that the percentage of males is in the population who would say yes to this question is greater than the percentage of females. So that's going to be my alternative. The percentage of ones in the mailbox is greater than the percentage of ones in the female box. All right? So now what do we do to test this? We can't poll everybody in the whole population, right? So we take a random sample, and that's what they did here. So they took a random sample of 500 from each box. And so n is equal to 500. And out of those 500, here n is equal to 500, and the sample percent that they got here was, what did I say, was, this is actually true data, is 31%. 31% of the men said yes, he should be confirmed. Versus how many of the females? Well, with the females, it was only 27%. So, 31% of the 500 men said yes. We got one, so they said yes. And only 27% of the 500 women said yes. All right, so now the question is, we have a 4% difference here, but is that 4% just due to chance variation? Meaning that every time we draw from this box, we're not going to get exactly the same percentage of ones. We'll take a new 500 and we're going to get something else, some difference just by the luck of the draw. And same here, we're not going to get exactly 27%. So how much that percent typically varies is measured by the standard error for percent. So let's figure that out. So let's figure it out for both of them. So remember, the standard error of percent is going to be what? The standard deviation of the box over the square root of n. So we'll figure it out for both. Now, in the denominator is going to be the square root of 500 for both. That's the square root of n, because the sample sizes are the same. So the only difference here is in the standard deviations. But a standard deviation of a 0-1 box is not going to vary that much. Let's check it out. What's the standard deviation of 31% ones and 69% zeros? So it'll be the square root of 0.31 times 0.69. That would be the numerator here. And here, it'll be very similar. It will be 0.27 times 0.73. So these are both approximately the same. This is about 2%. It's a tiny bit bigger, and it's just going to be a tiny bit smaller than 2%. They're both approximately 2%. Okay, so now how are we going to test these hypotheses? Well, what statistic should we use? Remember when we did the one sample z-test, we looked at the observed average or percent minus the expected under the null over a standard error. Well, we're going to do the same thing here. So what we're going to do is we're going to have our z statistic will be the observed difference between the two samples, which is 4%. The observed difference in our samples minus, what do you think? The expected difference. The expected difference under the null is 0. Over a standard error of the difference. And we're going to have to figure out how to combine these two standard errors to get that. So that's the standard error of the difference. So the picture we should be thinking about here is it's going to be distributed as a z statistic, right? We're going to try to get a p-value here. And we expect, under the null, if this was really true, we would expect a difference of 0%. 0 is a z-score, but also, this could be our z-axis, but also as a percent. So as a z-score and a percent. So here's our percent, 0%. And the question that we're asking is, even when the null is true, it's going to vary, right? Every time it's going to vary. How much it's going to vary? We'll follow the normal curve. And in standard units, it's going to look something like that. So the question is, this 4% difference between 4% that we saw minus 0%, the numerator is 4, where is it on the normal curve here? So where do we place 4%? Is it way out here, so unlikely to happen if the null is true, or is it over here? We don't know until we figure out what's the typical variation, the standard error. So we have to get the standard error of the difference, and that's what we'll get. Hold on. So the only question is, we know the numerator, we just have to figure out how to combine these two standard errors and get the standard error of the difference. So we know that the standard error, we have two sources of variation here. One coming from the male box and one coming from the female box. So we know that when we combine these two, we're going to have at least, we're going to have more error than from one box. Our standard error has to be bigger than that because we have another source of error. So it has to be at least 2%. You might think, oh, it's 4%. Why not just add them? Well, the key to thinking about this is to think about their two independent samples. So let me show you what I mean by that. All right? So here, we have for the males, we're looking at the difference. We have 31% for the males, but it can vary. Plus, the typical variation is plus or minus 2%. So that's for the males, and we're looking at the difference, so it's minus. For the females, it's 27% plus or minus 2%. In this case, they're the same. They don't have to be. Now, we know that 31 minus 27 is going to be 4%. That's our observed difference. But how is that going to bounce around? Plus or minus what? So plus or minus, this is the standard error for the difference. How are we going to combine those two? Well, let's think about it. You have plus or minus 2% here, minus another plus or minus 2%. Now, the largest it could be is if they're opposite signs. If this is positive 2 and this is negative 2, then you get positive 2 minus a negative 2, 4%, which is what you think might be logical, 4%. But that's the very largest it can be when they're opposite signs. When this one would be negative and that's positive, you get negative 2 minus 2, 4%. But that is only going to happen by chance. It's not, if they're independent, they're not linked. The errors here aren't linked. If they were completely negatively correlated, so if you get 30, plus 2 here, negative, you'd get minus 2 error there. They'd have to be perfectly correlated with each other. But they're independent. What happens here, however many ones we get here, does not influence in a random draw however many ones we get here on any particular random draw. Why would it? It's not like the boxes are speaking to each other, right? So the idea is what? It's going to be bigger than either one of them, bigger than the 2% in either one of them, but smaller than the sum. And one way you can remember this is by the Pythagorean theorem. You can think, okay, if the errors are completely independent, and a way to draw this, they call it orthogonal to each other. They're completely independent. They're not both going in the same direction or both going in the opposite direction, but completely independent. Knowing the direction of this one doesn't affect the direction of the other one to either be this way, anti-correlated, or positively correlated, or any correlation at all. They're completely independent. So think of them as direction-wise, orthogonal to each other, right angles. And so then you can think of the standard error of the difference as the sum of their squares in a Pythagorean triangle. Like if this is A, and this is B, and this is C, A squared plus B squared equals C squared. So C is the square root of A squared plus B squared. So in this case, it would be the square root of 2 squared plus 2 squared. So let's write that down, and there's a proof for it in the back of your notebooks. And that you should, it's a simple proof, mathematical proof that I strongly urge you to look at. All right? And so our standard error for the difference, back here, we can say we need some more space. I'm going to erase this right here and say the standard error for the difference is equal to, like the Pythagorean theorem, it's the standard error from one of the samples, I'll call it the male sample, squared plus the standard error from the female sample, squared. And that's true as long as the samples are independent. That's a key concept. Another way of expressing this, these are variances, that the variances sum, but the standard errors, the square root of the variances, don't sum. They're the square root of the, okay? So that's what we have. So in this case, what should we put in the denominator? Well, it would be the square root of the standard error 2% that squared, plus, they were the same, 2 squared, which is equal to the square root of 8, which is approximately, the square root of 8 is 2, a little bit less than 3, 2.83. So that's what's going to go in the denominator here. So this test statistic, our z-score, is what? Z equals 4 minus 0, 4 divided by 2.83. So now as soon as you see this, you know where that 4% is going to be on this curve. This is equal to 1.41. So 1.41, so it's not on this, so 4% matches up, it's not way out here, it matches up with 1.41. That's where 4% is. As a percent, it's that, but as a z-score, as a pure unit, it's 1.41. So our p-value is the probability that we would see if the null was true. If it's true, the probability that we would see such a big difference in this direction or even more. So we can look that up between 1.41 and negative 1.41 on our table. That's negative 1.41. And draw it that accurately. Should be a little bit closer to the negative 1, right? All right, between those two is 84%. So now we just want this area here, and this area is going to be 100 minus 84, which is 16 divided by 2. If you'd say the whole thing is 100, so you take out the middle, which is 84, so these two together are 16, but we only want one of them, so this is 8%. So that's our p-value, 8%. So what is our conclusion here? Hi, so here we are again, and we got this. This is our z-statistic, test statistic, 1.41. We saw for a one-sided test, we get p-value of 8%. So let's look over here. So 8%. That means if the null was really true and there was no difference, 8% of the time we would get a difference of 4% or more. A z-score 1.41 or greater. So if we set the cutoff at 5%, we didn't get beyond that little bit of doubt. We didn't get beyond a reasonable doubt here, right? We have enough doubt that we don't have enough evidence to reject the null. We don't have enough evidence to, so we can't reject the null. We cannot reject the null. We can't convict, basically. We just don't have enough evidence. We almost do, but we don't have quite enough evidence. Cannot reject the null if we, at 5%. If we set, if significance level is 5%, if we set that 5%, which is a very conventional cutoff, we cannot reject the null, so we conclude we don't have enough evidence we don't have strong enough evidence to conclude that this difference that we see that would hold up in the whole population. We don't have enough evidence to conclude that males and females would answer this question differently. If you poll all of them, that males and females in the whole population, not just in our sample, so I'm surprised, actually pleasantly surprised. I thought for sure there'd be a really big difference, and I was The data says otherwise. Now what they're saying, what they'd actually believe is it might be a different question, but all we can go on is what they say. So this is a really good example of how statistics can keep you honest. Because I probably, if I didn't know statistics, would have seen that difference and would have just said, oh, you know, without even really thinking about it very much, you know, just become convinced that the data shows that male and females are really different on this issue, and maybe they're not. So it opens your eyes and allows you to be more objective. And I hope that's how you'll use statistics too. That's the end.